see you. So last lecture we finished discussion of AC electric circuits. So now we know how we deal with AC current and consider all elements of AC electric circuits, which is electric resistor, inductor, and capacitor. We figure out that there are some phase shifts between current and voltage depending on which element is introduced into electric circuit, and in the case when we have all of them integrated together and connected in series, we have some resultant impedance which tells us the opposition of electric circuit to AC electric current, and that is described by the magnitude of active resistor, like square root of active resistor in second power plus difference between the inductive and capacitive reactance in second power under this square root. So that's magnitude of impedance, which defines the position of AC electric circuit, which consists of active resistor, inductor, and capacitor to the flux of charge carriers, like AC electric current. So today we continue our course with a new chapter, that's electromagnetic waves. And last lecture we had this question regarding the topics to be covered by the Viktor, like this exam which is coming. So it will be AC electric circuits, electromagnetic waves will be already for the last one. So this current topic which we discussed will not be included in the exam. So electromagnetic waves, obviously we are going to deal here with combination of electric and magnetic fields and consider them as varying in time and being sources of each other, so generating each other. This feature allows electromagnetic waves to propagate in free space where we don't have any medium, so they can generate each other and spread with certain speed in vacuum in free space. So this speed is known to be speed of light, so there is obviously a clear relationship between general electromagnetic waves and light, which can be the speed of light can be experimentally measured. So it was initially predicted theoretically that electromagnetic waves can spread in free space with certain constant speed, and later it was shown experimentally that the speed of light is actually equal to this theoretically determined speed for electromagnetic waves. So this statement is considered to be very important because we have shown the relationship, nature, the physical nature of electromagnetic waves and light. So light actually is a form of electromagnetic waves in certain spectral range. So these theoretical calculations for determining the speed of electromagnetic wave propagation in vacuum was carried out in the scope of Maxwell equation, like system of Maxwell equations. There are 4 Maxwell equations, and we will definitely consider all of them and also try to determine predict what is the actually speed of electromagnetic waves propagation in free space. So before we discuss whole system of Maxwell equations, we need to consider one small but very important modification of Ampere's law, which takes into account so-called displacement current. So far, we had discussions of uh, conductivity current, but there is possibility when we need to consider also displacement current. So who will remind me what is Ampere's law, how we write it? So integral over closed path of the product between and ds will be equal to mu naught times I. And that's conductivity current. So what does it tell us? That the integral over some closed path of this scalar product B vector ds vector will be equal to mu naught magnetic permittivity of free space times conductivity current, which flows through the area defined by this closed path. So now let us take a look at this slide. So what do we see here? We have some current which flows through the conductor and capacitor. So now we consider this path, this closed path. And it's possible to consider two surfaces, like one surface S1 blue and this orange S2. So both of them originate from the same closed path. And if we consider now first surface S1, what will be the current which flows through the surface S1? It will be just I, the conductivity current, which is carried through this conductor. However, if we consider this surface S2, then what will be the current? Do we have any conductivity current between these two plates of a capacitor? No. It's insulator in between these plates. So either it's just free space, vacuum, or it's filled with some insulator. So under ideal conditions, which we consider, we don't have any conductivity current there. So what it means that we consider surface S2, current through the surface will be equal to 0, and then integral of scalar product B vector ds vector over closed path will be equal to 0. So what we get, let's write it down here. Maybe we can even write here, yes. So for S1, we get integral over closed path B vector ds vector will be equal to mu naught times I. For S2, integral over closed path ds vector will be equal to 0, since current is equal to 0. So this brings us to some contradictory. That doesn't make sense because we have to keep in mind that current possesses this continuity feature. We cannot have discontinued current flow, and that comes from originates from the law of conservation of electric charge. So we have contradiction here, and we need to deal somehow with this. So in order to solve this problem issue and proceed further with the complete Maxwell equations, system of Maxwell equations, Maxwell proposed so-called displacement current. So let us come back to our whiteboard. And displacement current we introduce as epsilon naught times first derivative over time for electric field flux over time, like first derivative over time. So that is the additional component which was added by Maxwell to Ampere's law, and then it transformed to Ampere's Maxwell law. And in this case, we can represent the Ampere's Maxwell law as follows: integral of scalar product magnetic field vector ds vector is equal to mu naught times conductivity current plus displacement current, and that will be equal to mu naught times conductivity current plus epsilon naught dFe over dt. So this is Ampere's Maxwell law. So why this is important? Because it solves this problem which we highlighted on previous slide. And no matter where we consider this surface of the closed path, we always will get the same current flowing through the um, surface. So we will show a little bit later that indeed, if we consider some capacitor, let's say parallel plate capacitor, we will have this displacement current equal to conductivity current. So how it actually can be processed? So we consider a capacitor attached to some conductor, and here we have some current I, conductivity current in the conductor. So this will cause charging or discharging of parallel plate capacitor, and that is will be defined by the direct, like initial state of the capacitor, if it's charged or discharged, and also direction of the current. So that's not important. Important here that this will change the amount of electric charge which is accumulated at the plates of this capacitor. So we will have charge accumulated by a capacitor as a function of time. So we will deal with some instantaneous magnitude of electric charge accumulated in capacitor at any moment of time. So that could be represented as sigma as a function of time, means surface density of this electric charge times area of the capacitor. Area of the capacitor is constant parameter, but sigma obviously will change as we charge or discharge this capacitor. So if we have any charges at the plates, there will be electric field created inside this capacitor. And as a result of varying amount of charge accumulated in the capacitor, we will also observe time-dependent electric field. So this electric field vector will be the same in orientation, will be just perpendicular to the plates of the capacitor, but its magnitude will change over time. It will also possess some time dependence. So this varying electric field inside the capacitor can be considered as a source of magnetic field. And that's why the integral, when we take this integral of magnetic field vector over closed uh, path, should take into account contributions from both conductivity current, which is classically known as a source of magnetic field, and also this displacement current represented as the first, like the rate of electric field flux change over time times permittivity of free space. So now if we consider specifically a parallel plate capacitor, electric field will be represented as charge Q accumulated at the plates divided by epsilon naught divided by area. So in other form it will be sigma divided by epsilon naught. Can even write it here, sigma divided by epsilon naught. What will be flux of electric field? In case when we consider parallel plate capacitor, so this case, we have electric charge, which creates electric field, and some surface perpendicular to the electric field vector. So since electric field is uniform and this surface is perpendicular, we just have product of electric field and area of this plate of the capacitor. So now let us come back to whiteboard. So we can represent it as electric field magnitude times area of the capacitor. And taking into account expression for electric field, so we can substitute it here, we get that it is Q over epsilon naught. So this is the expression for electric field flux. Now, if we consider expression for displacement current, by definition, that's this equation. So it will be epsilon naught times df e over dt. So what it will be? Epsilon naught times dq over dt times 1 over epsilon naught. So we just substitute instead of fe expression here in the derivative. And we cancel out this epsilon naught. We end up with dq over dt. And what is this? It's conductivity current which flows through the conductor. So we can write that it is equal to I, and thus we show that displacement current in this example is equal to conductivity current. No matter which one we take, in this case, first term or second term, we get the same value. So doesn't matter which surface we consider, surface 1 or surface 2, which we discussed at the slide at the beginning of our lecture, we will always get the same magnitude of this integral. But in both cases, there will be different origin, like source of magnetic field. In first case, we will have just conductivity current as a source of magnetic field, and in the second time, it will be time dependent or time varying electric field inside the capacitor, which results in so-called displacement current proposed by Maxwell. So now when we modify the Ampere's law by adding this concept of displacement current, and we end up with Ampere's Maxwell equation, we can proceed further and consider a system of Maxwell equations in free space, where we have not just vacuum, means we have just permittivity, electric and magnetic permittivities of free space. We also don't have any charges in this. So when we specify free space, that means free of any charges also, not only some medium. In this case, we consider that charges are equal to 0. Write it here. Q is equal to 0. And then obviously electric current will be also equal to 0 because there are no charges, no electric current. So that will be the condition which we apply further to a system of Maxwell equations in order to determine the speed of propagation of electromagnetic waves in free space. But now we will go for general case for vacuum of system of Maxwell equations. So what equations are included into this system of Maxwell equations? So first of all, we have equations integral of dot product electric field vector dA vector, and that is equal to Q over epsilon naught. So any comments on this equation? Have you ever seen this? What is this? Gauss law for electric field. Exactly. So we have a statement that integral over closed volume, like closed surface, which defines some volume, will be like of this scalar product of electric field vector and dA vector, means the vector perpendicular to the elemental surface, and its magnitude is defined by the area of this element, will be equal to electric charge confined in this closed surface divided by epsilon naught. So that is the first equation of our system, and actually what main message it brings to us, that the source of electric field is electric charge. So electric charges are sources of electric field, and we have electric field lines originated at positive charges and terminated at negative charges. So that's why it is possible to get this condition for Gauss law in the case of electrical field. So second equation is similar, but already for magnetic field. So we have integral over closed surface, scalar product of magnetic field vector times dA vector, and that is equal to what? That should be equal to 0. So we have discussed this question some time ago, and Gauss law applicable to a magnetic field tells us the following. So because of the absence of so-called magnetic charges or magnetic monopolies, we do not have origin and termination of magnetic field lines at some points. These magnetic field lines, they are closed, they don't originate and don't terminate anywhere. They are closed, they just come out from north and go into the like south pole. So taking this into account, we cannot place inside this closed surface any magnetic charges since they don't exist, and by definition we cannot get any value of this integral, this flux of magnetic field through the closed surface, because as opposite to electric field we have sources like electric charges which are sources of um, electric field, and it's necessary to take into account either we have positive or negative charges inside the closed surface, because it will be this net flux will be positive or negative, since electric field lines originated positive charges, so then flux will be positive. But if we have negative charges, they terminate on the electric charge, so it will be already with negative sign. Here, for Gauss' law applicable to magnetic field, we just get zero. So that is the second equation. Now let us consider the third equation, and that is integral over closed path of scalar product electric field vector ds vector equal to minus df b over dt. So what is this? As Faraday's law. So Faraday's law, we considered it earlier. So in the left side, it's actually the electromotive force for closed path. And this electromotive force is defined by the rate of change of magnetic field flux over time. So what is the main message here? That varying in time magnetic field, which defines magnetic field flux, is a source of so-called induced electric field. So now we can consider like equation 1 and 3. We can claim that they describe two options for like sources of electric field. Either we deal with let's call it electrostatic case, when electric field is created by electric charges, or electric field is created by time varying magnetic field flux. And the last fourth equation will be the following: integral over closed path of b vector ds vector will be equal to mu naught times I plus epsilon naught times mu naught times df e over dt. So yeah, if I guess here I forgot to put mu naught. Yes, we open this parenthesis because just ID is this equation. So this is Ampere-Maxwell equation, which we discussed at the beginning of this lecture. So now, let us specify here that there are two type of sources of electric field. Electric charges, and time-varying magnetic field flux. At the same time, when we consider equations 2 and 4, the second equation tells us there are no such options as magnetic charges. They cannot be less. They cannot be sources of magnetic field. However, at the same time, we still have two type of sources for magnetic field, and they originate from equation 4, which is Ampere's Maxwell law. So first source is conductivity current, and second source is the time-varying electric field flux or time-varying electric field. So these are the main messages of the system Maxwell equations. We have four of them. Usually, we can add one more equation, which is not really like part of Maxwell equations, but quite often is used to provide complete information about electromagnetic field. And so that's for Maxwell equations. They provide complete information about electromagnetic field, but sometimes we also need to provide information on the forces which are exerted on electric charge placed in this electromagnetic field. So that is so-called Lorentz law. And we can write that the net force exerted on an electric charge placed in electromagnetic field will be equal to charge Q times electric field vector, which is electric force, plus magnetic force, and that will be Q times velocity vector cross product with magnetic field vector. So together, like these four equations, this is a system of Maxwell equation, and this one is Lorentz equation. Together, they provide complete information about electromagnetic field and also force exerted on electric charge placed in this electromagnetic. So our next step will be the derivation of speed of electromagnetic waves propagation in free space. So again, we will discuss a little bit today what we consider, and we will do that to like next time because it requires some time. So we don't interrupt. So we need to consider free space, which is vacuum and absence of any charges. If there are no charges, so charges will be equal to zero, and the conductivity current, also will be equal to zero. So with this approach, we will consider combination of Maxwell equations in order to get the expression for the speed of electromagnetic waves, and the magnitude of this speed of propagation of electromagnetic waves in free space will coincide, as shown experimentally, with the speed of light in vacuum, and that is a very good uh, experimental proof, match between theory and experiment, which shows us the nature of light, which is electromagnetic, which can be considered under some conditions as electromagnetic wave. So now let us summarize our discussion for today, because we introduced quite important concepts here. We considered Ampere's law at different cases when we have conductivity current and displacement current, which introduced by Maxwell. So we have shown that if we don't consider displacement current as this addition provided by Maxwell, we have some discrepancy which leads us to discontinuity of electric current, because if we consider surface of a closed path which cuts the conductor, then we have conductivity current. But if this surface goes through the capacitor, then we obviously don't have conductivity current, is equal to zero, and Ampere's law gives us this integral over scalar product of B vector ds vector gives us zero, which is not matching with the previous result when we got mu naught times r. In order to fix this problem, additional component was added to the term, was added to the Ampere's law, which is displacement current, which represented as epsilon naught times the rate of change of electric field flux over time. And now we have two terms which solve this discontinuity problem. No matter where we consider this surface through which electric current flows, it will be either conductivity current or displacement current, Maxwell displacement current, which gives us the same. We have shown that these currents are equal to each other. So then we consider the system of four equations, which are called Maxwell equations. We have first equation that is Gauss law for electrical field. It tells us that source of electric field can be considered as electric charge. Second equation, that is Gauss law for magnetic field, tells us that we don't have any magnetic charges. That's why it's equal to zero. So for magnetic field, we cannot consider any charges, magnetic charges as source of magnetic field. The third equation is telling us that the induced electric field can be created by time varying magnetic field, and that is the second type of source for electric field. First one is electric charge. Then the fourth equation is the Ampere's Maxwell law, which tells us that there are also, nevertheless, we don't have magnetic charges. We still have two types of sources of magnetic field. One is conductivity current, another is time varying electric field. And this system of four equations is completed by the fifth equation, which is Lorentz equation. It tells us the net force exerted on electric charge placed in electromagnetic. So the combination of these equations provide all information about electromagnetic field and forces exerted on electric charges, which is important. But the main message to take home from here, that looking at the system of Maxwell equations, we need to clearly see what it, like the main conclusion out of it. It clearly defines the possibilities of creation of electric and magnetic field. So there are two types, there are two sources for electric field and two sources for magnetic field. So that's what you definitely need to remember. So we will continue with derivation for speed of electromagnetic wave propagation in free space next lecture. Now, thank you very much for attention and have a good evening.